Alaikum guys, we're gonna continue talking about energy, and may you have all the energy you need to review for your exam. Elastic potential energy. Its formula is very similar to the formula of kinetic energy in that it has a half and it has something squared. So potential elastic energy, S for elastic, is half k x squared, half kx squared. Okay, so this is a spring, okay, that this is its length at the beginning, and then I'm gonna compress it. So I compressed it by this x is the compression here. This is a compression. Some people and some books use, instead of x, they use delta x, and that's fine also. The formula would be PES equals half k delta x squared, where delta x is the compression or the stretch in the spring. Guys, the delta x or the x needs to be expressed again in meters, you know, in the SI unit. So if you have it in centimeter, you need to do what? You need to divide by 100. This way you convert it from centimeter to meter. I have never seen a spring that is compressed by a kilometer or 2 kilometers or stretched by that kind of distances, so you wouldn't have to convert from kilometer to meters. It's basically, you know, springs are not very long, so you compress them or you stretch them by centimeters. That's why you need to know that 1 centimeter is 1 meter divided by 100. You see here the centi. Okay, centi, it's 1/100. In French, they say centimètre, okay? Just to lighten your revision a little bit. Okay, so now that you know what the potential elastic energy means, so it is the energy that we store in a spring if we compress it or if we stretch it. Does it matter if I have a spring and then I compress it by x, or I stretch it, so this is compressing it, or if we stretch it by the same amount, by the same so this is a stretch by x, let's say 2 centimeters, and this is a compression by 2 centimeters. Does it matter whether we compress it or we stretch it by the same amount? Does it matter in the formula how much energy we store? So potential energy elastic is half kx squared. So your x is going to be squared. So whether it is a compression or a stretch, if it is the same quantity, the same distance, it doesn't matter. Your spring is going to have the same potential energy. So it doesn't really matter whether it's a compression or a stretch, half kx squared, or again, in some books, some colleagues use delta x squared. I just, you know, like not to have, I just want my formula to be simple and elegant, you know. So I don't like to use the delta, but maybe some teachers and some books prefer the delta, and that's perfectly fine. Okay, so it doesn't matter whether it's a compression or a stretch. You will store the same energy in a spring if you stretch it or compress it by the same distance. Okay, let's take some example. And what is the K? What does the K mean here? The K is the spring constant. So every spring, like every boy in my class has a name, every spring would have a spring constant. That is its identity, or the spring identity. So if let's say 1K is 10 Newton per meter, and one spring has a spring constant 10 Newton per meter, and another one has a spring constant of 200 Newton per meter. Which one do you think is stronger? Which one do you think is stiffer? Which one do you think is harder to to stretch or compress? Is it the 10 Newton per meter? This, you need to apply a force of 10 Newton in order to compress it or stretch it by 1 meter. This guy here needs 200 newtons to be stretched or compressed by the same amount. Of course, definitely you guessed it and you're right. The higher the K, so this one corresponds to the stiffer spring. So the higher the spring constant, the stiffer or the stronger the spring, and the harder for us to stretch it or compress it. So now we are done with the spring constant. Let's do some calculations, and I can assure you they are super duper easy. Okay, so let's hit it. So I have potential elastic energy is half kx squared. Let's say we have a spring that has, we're gonna simplify our lives, K equals 10 Newton per meter, and then you stretch it by X equals 1 centimeter, okay? So first of all, what do? The centimeter here, we're not going to leave it into centimeters. We're going to convert it to meters. And what do we do from centimeter to meter? Centimeter is much smaller than the meter, so we need to divide. So it's going to be 1 meter over 100, or 0.01 meter, or scientifically 10 to the negative 2 meters. So the potential energy stored in that spring is going to be half. The K is 10, and then the X is 0.01, or I prefer to write it 10 to the power minus 2 squared. Okay, guys, so what do you do in your calculators? You take the X, you square it, then you multiply by 10, then the whole thing you divide it by 2, or you multiply it by 0.5. So this guy, when you square it, the calculator will give you 10 to the negative 4 times 10. I hope you know your exponents. This is going to give you 10 to the negative 3, and then either times 0.5 or you divide it by 2, and this is just going to give me 0.5 10 to the negative 3, but if I want to write it in the scientific way, then it's going to be 5 10 to the power negative 4 joules. See? This energy here is 0.005 joules. It's much less energy than if you, with 60 kilograms as a mass, go up by 1 meter. You would be storing, we said, 600 joules. So compare it to this, it's just 0.0005 joules. However, if the spring has a higher spring constant, let's say 1,000 Newton per meter, maybe the springs in your car, I encourage you strongly to go and find out about the springs in your father's cars. What is the spring constant for those coils? Then if you compress it by maybe a centimeter or 2 centimeters, you would definitely be storing way more energy than this. So that's it for now.